Okay, so hi everyone, I'm João, that's Luís Gomes. We're here to talk about practical out-of-band data exfiltration in 802.11. That's Wi-Fi, for anyone who may not have heard of it before. I've pretty much have some bio things here. Mine's a little bit more serious, Luís is a little bit better. So I work at Checkmarks, I work at Cobalt as well. I co-developed Airpone NG, which is a man-on-the-side attack tool on wireless as well. I built a couple of tools. Well, actually, it was more like a module or two for Metasploit too. So I was a DEF CON 25 workshop instructor. I did a workshop about Scapy, which is also the framework we built this tool on. So things should get interesting. And Luís, would you like to introduce yourself? Or just show you the money? I don't know.
So for me, I'm currently head of security for OLX and the Nasper group. I also work at Cobalt. I started in the banking industry or payments industry with SIBS and then moved forward to do a couple of things in my life. But ultimately, currently I'm just doing bug bountings. Shout out to Sopas, and also taking care of the security in OLX. So,
okay, so let's get down to business. First of all, let's do just a little bit of an intro. 802.11 has several frame types. This is pretty much what the format is. When you have the type and the subtype actually dictate what the type of frame it is. If you have control frames, data frames, and there's the management frames as well. What prior art in data exfiltration through out-of-band channels in 802.11 has done is actually grab one of these many fields and try to manipulate them and insert data there where they will not be used or would not be checked or something like that. So this is pretty much what we want to do. This is your typical 802.11 network. You have a Wi-Fi router, you have the internet on the other end, and then you have the devices you have internally. What we want to do is something like this. So you drop an implant, there's a physical cable, usually it's a cable connection from the implant to the router. And then there's an attacker device that gets some kind of signal or response or whatever communications through a channel that's parallel to the actual server you're trying to use. What are the benefits of this? There's many. You don't go through their IDS or IPS or whatever. You don't send packets through their network. You can even get to a point where the wireless implant does not have an IP on the network, and yet you can still port scan or do whatever you want. And still get communications outside without anyone on the inside having any idea what's happening. So this is pretty much what we want to do. And now what's the problems we might face, or the real point of this is to get communication and data across without being detected. So even though the prior art has done this semi-successfully, the very first idea or the very first thought of how to implement something like this would probably be the level 0 attack, which is the easy way. Just drop a rogue AP, right? So you just drop something there and connect it with a wired or wireless to the on-scope AP, let's call it that, or the target AP. And then it just spins up another AP, and you can just connect to that through your attacker device. And what else would you need, right? Well, there's a problem with this approach. Well, while it's out of band because it's not really on the attacked network, the beacon frames sent by this AP, which is in this case the Wi-Fi pineapple, will pretty much give you away, because if somebody's doing defense on the wireless side, they will immediately detect that a new AP has popped up and is sending beacon probes and sending you all these packets so that it shows up in your device list when you try to connect. So pretty much this is something that was the state of the art, or trying to be the first way to do it. But then you start to get into the more technical things on how to hide data inside the actual frames. And now I'm going to pass it on to Luís to keep going on the other parts.
So, yep. So what we have right now is, well, we have some stuff right now that is similar to what we are about to show. Still, it's not that easy for a blue team to detect, but depends if the team is, one, skilled enough, two, if they have enough tools to detect it. But above all, just the critical point is anybody looking at what you are trying to send out? I think the famous one will be Spider Lab's got one called Smuggler, and there is patents already, or something similar about scenography. We have exfiltration patents on devices similar to what we are about to show, and there is also the one on the left, on your left or right, that is pretty much a library that assumes that creates UDP channels, and it's similar to ours. And we're going to show on the next slides that everything is, these are nice implementations, still flawed by design, because if you will create an agnostic layer between what we are looking for, and you don't look for signatures or attacks that are specific using encoding or whatever you're going to think of at the end, you're going to understand. But right now, the critical part is most of them use either A, something that you can detect just by looking at Wireshark or CM or any other monitoring tool that you have, or B, if you have some kind of AI just looking for patterns, is going to spike right through it. Like, you're going to see all the communications and don't work, because at some point the blue team is going to understand that something is off, because either A, there is like you said, either a rogue AP or one AP that has the same name as any other is sending too much data, encoded data on strange fields, or it's doing everything right, but got always the same destination, always the same fields, never random, fields always static. So that is one of the ways that you see that don't work. Well, you have one of the levels that is surely, yeah, you're going to show.
Okay, so this is one of the means that have been used before to send data out of band. So as I was saying before, the problem with the Rogue AP is that it's constantly sending beacon frames with the SSID name. So here I am Microsoft guest wireless. So that it will keep sending those like 10 every second or something like that, so to make sure that it shows up in your device list, Wi-Fi access point list. What some people found out, namely the guys from the Spider Labs, is that you can actually send just one of them, and instead of sending an SSID, you just send data there, like base64 encoded, which is what they did. So they actually implemented it. I think we can probably show a demo of this. Okay, so let me just try to... Okay. Can everyone read the screen? Consegues aumentar o tipo de letra? Acho que sim. Acho que comando mais, ou control mais.
Não.
No?
Nope. Estás em acesso. Ele não consegue ler.
Let's hope it's possible to read.
There.
Okay, so this will be the server. So you would have to set up the receiver. Sorry. Then you set the interface name, and then so on one end you have the server, and on the other end you have the attacker. So what you have is this is the implant, and that's the other device the attacker is going to use to exfiltrate data to. In this case, we'll see very fast why this is a problem. So it will try to, pretty much what it'll give me is a shell. Let me just try to pull this up for you. Okay, so pretty much what they give us is a shell. If you do ls, in theory, it would be getting the, let me just check for 1 second. Yeah, right. Because for this to work, both cards have to be at the same channel. So since that one was channel hopping, it probably wouldn't work. Okay, so as you can see, it got actually a bad command, but it's fine because this is kind of okay. So now it works. You see ls, they cannot access something. So this is actually just the proof of concept code. I just literally git cloned it and tried to use it. So this is the experience you have. ULS, what it does is it runs your command, grabs the output, waits for 5 seconds, then sends the response back. As you can see, it was just there, right? So this is what they had, right? So there's a bit of a problem here. So let's try another command. Let me just exit so I can pull the screen up. So let's try a command that has actually a little bit more of an output instead of just 3 lines or 4. Yeah, that's not going to work. It's just going to say, yeah, no, exception, so yeah. UByte format requires 0 or something, just 250-55. Okay, so this is what happens when you try to just use a tool that's already been worked on. This is supposed to be the state-of-the-art of open source out-of-band data exfiltration in wireless.
Yeah, so why? Well, this is what if you grab the PCAP, if you are looking at the traffic right now, I don't know if some of you do blue team or not, but even if you don't do blue team, like if you look at the SSIDs on this part of your window, tell me that if this is normal, like if you're just looking at normal patterns and that is what we are talking about, this over here or on in here depends on where you want to look at. If you don't get spiked by this, then something is wrong. Like you need to understand that if this is your state of the art of exfiltration, then you need to step your game up because this is not going to work in any organization with proper. We're talking about in the end of the slides, we're going to have military grade exfiltration. Like we're talking about when you want to do something right, not get caught with it. So normally what we are thinking is, and this is for people that know me, this makes sense. So this is, you want to get like the maximum amount of data that you can. Like João just showed that he can't like bring a big information outside because it's limited to the size that he can exfiltrate. But the thing is, we want to get all the things that we have there. Doesn't matter if you want to just have a foothold on the organization and just
wait for it.
Use as a shell or whatever you want. But the number one reason why these tools don't work is that they don't know how to disguise themselves. Like, you need to understand that if you want to get by any AI in the future, or if you want to get by any detection measure, you need to be expected to be detected, but at least act like a octopus. Just understand what is the texture, the feel, the looks, and be like that all the time. And do not spike any type of thresholds on patterns, because at the end of the day, and we're going to show a little bit of improvement from the state of the art that they have until we show you the big boy, is you can really just disguise, like you can take from that specific spike that you see in the SSID, the exfiltration, and use other fields, like he showed you the fields before, just to give an idea where you can try to put your payloads to exfiltrate that or just to interact with the shell. But at some point, if somebody, like we are presenting now, in the future, if we present in more places and the tool becomes famous, people are going to start looking at the solution and they're going to create rules, right? So what we're going to present in the end, and this is just an improvement from the example before, is a way that either if they improve, doesn't matter how they improve it, 10 or call Watson or whatever they can call it to try to track our tool, we're going to be a step ahead and just blend in more to the part where you can be exfiltrating data and not get caught. Or if you want to get caught, just in the end of the talk, I don't have nothing programmed to dinner, and for some numbers, we can already see some kind of detection. But until then, it's undetectable. Or if somebody got an idea in the end, please feel free to break our tool. Yeah.
Okay, so let's get a little bit into the specifics. So, as I told you before, the other ones used additional ELT layers on the 802.11 frames, or replacing the SSID field with the data you want to exfiltrate or whatever. So let's try something different, just a different approach. Let's use 802.11 data frames. They were actually designed to hold the data. So if you're doing like a GET request, that's where the GET request will actually be. And they're usually encrypted because usually Wi-Fi networks have encryption. So you're just going to be looking at random data. So that doesn't matter because for us, what we really want to do is not stand out. So how do we use a data frame and not stand out that somebody's sending something outside of our network? Well, let's just take a little bit of a look into what the structure is of this packet. So it's this is just a QoS data, so it has like the data over here. This specific packet has just 155 and 45 bytes of length. It has some CCMP parameters because that's the encryption that was used on the Wi-Fi network. Some addresses just to know who is sending, who is receiving, and then there's not a lot else. So it's kind of simple. Let's see what this will look like for the attacker. So they would just drop the implant, connect it to the target, and then send the data frames up to the other device. How is this different from what we just showed you before? Well, this is what the defender sees. The actual implant, what it does is it scans the neighboring APs, picks one that's at the appropriate signal strength, and then tries to emulate that AP is sending a message to another station that's even further away that you can't see. So you can just, for the defender, they can just assume that they can only see half of the conversation. Because they're closer to the AP, the station is even further away, so they can only see half of it. And that's like the server talking, and when the client talks, it's the other AP. So the client will do the exact same procedure. They will look at the airspace, they will try to find an AP to spoof, and then just start sending packets. But there's a little bit of magic here. Like, for example, how does Wi-Fi Station 2 know how to talk to Wi-Fi Station 1? Are you using hard-coded MAC addresses? No, because then you can track me. So how are you figuring this out? Well, there's some magic called TOTP, which is the technology behind your Google Authenticator codes that roll every 30 seconds. So basically what's happening is this wireless implant is just sitting there quietly, iterating its TOTP algorithm every 30 seconds. And in the correct time slot, when the attacker's device tries to connect, it will see if the MAC address, which is deterministically generated via the TOTP secret, matches with what it's expecting. It will send it will accept the packet and send the response. With another, it will hop channels. So this is set for a default channel of 6. If it's in channel 6, it will be ready to receive a new connection. At the point that it receives a new connection, it will just send a handshake packet that will say, okay, this is the MAC address I'm going to use because I already saw this station 2, which is an actual station talking to AP2, neighbor AP2. So let's just try to spoof that. And now the question is, and this is why Luís was asking, how do you detect this? The question is, how do you know when you're trying to protect your company, which is target AP, that AP1 from the neighbor is talking to Wi-Fi station 1? How do you know if that's a legit station or not? Is that in scope even? Should you try to even track the neighbor's AP? I think the asymmetry of the attack and the defense on this kind of wireless exfiltration via out-of-band channels is kind of makes it really hard for the blue team to actually track this, because this is just one of the ways that you can do it. You can do it a million different ways. And if you try to make the algorithm secret, and that's the key, the secret sauce to your solution, then once somebody buys it or picks it up, then you're done. If you actually have something that people know how it works and you still can't detect it, then you got something. And I think that this is a very nice solution. It will not work in every scenario, because if you have a Faraday cage and a very secret underground vault, then you will not have a neighboring AP, so this will not work, right? But there are many offices in high-rise buildings or just in a regular office building that has a lot of neighbors and a lot of APs in the neighboring airspace. So this will probably work in 99% of the situations. Luís, do you want to talk a little bit more about the detection?
Yeah. So most of the times, the exercise that me and João were having for almost a year now is either I think I develop a way to detect it, and he tries to break it, like evade it. We do that exercise probably once per week. So my question is for everybody this is a lot of information for a slide first. I know for a top. The thing is, this is all the variables that I gotta think about when I'm trying to detect this type of attacks. These are from to are expected. The time is is these two APs talking at the time there is no one in the office or is supposed to have they are supposed to be talking at that time. This is so many information, but this is all the vectors that I gotta look, and then from all these type of questions that I can ask myself to create a detection for the type of attacks that you see right now, then we have different sources of data sources, like can be from the type of exfiltration that he's trying to do is coming from the implant, but when you're trying to construct the rules, what you see is the thing over here. So logical conditions to over something that I don't know if I'm not even looking at, or trying to create a logical condition that will tell me that the network events that are happening will result in an alert is very hard because everything he's doing is expected. So there is no type of a difference that I can look at a healthy communication between two APs and say, well, this is something that we can detect because this has never happened before, or I never seen this before, or this can happen from time to time, I don't know when, but I should review the event every single time that it happens. It doesn't happen like that. The last version that we have from the tool only acts when there is people hacking, only sends packets that are expected. If you look at RFC from the protocol and look at our package, and on the end, feel free, he's going to have a cell phone there, and you're going to see our last version. You go to the table, and this is our military grade. This is an example of a cell phone that he has right now on the hand. You can go, imagine, drop the implant. You can go there and check it. You drop the implant and you go pass by the office on the street. You can interact with the shell and either exfiltrate data or recon the network from the outside, like in Starbucks, just on the front of the building, and interact with it. The problem is nobody's going to detect you anyway because everything that is going out is expected. So because they don't even know that the packages that are going out are being used to exfiltrate data at all. So my main slide about this, the point of having this slide is blue teams right now, the increase of complexity is pretty hard to deal with because we have more and more data to look at it. Even when you use AI is looking for patterns, and the guy that is supposed to be the brain of the operation is looking for stuff that the AI can't really recognize. And even the guy that is looking at events that is supposed to be detected, he can't see anything. If you see we can show you the PCAPs there. This is too much in terms of information on a PCAP for me to show you. But if you show the PCAPs, and you can feel free to download the code and try to use it and detect it, you can't really see on the PCAPs anything that I showed you before that is spiking. Like you go for every field, every single field, and you can't see a difference from your package and João's package. It's equal. The difference is it contains the data that is valuable for your company, and I don't. I'm just telling, hey, connect to me. Hey, do you want to connect to me? So now he's going to show you our ultimate military grade, and Scretas or anything, if you're here, you know. I'm here. I mean,
show me the money.
Show me the money. Yeah. So after the talk, please feel free. I beg you, just go there and test for yourself the execution and try large commands, stuff that you see that flawed on the others. And if you feel that is a weak implementation, use we're gonna share the code, use it and try to break it. That's our model.
And this will be public on a GitHub link that we will share with you guys. So a pull request is always welcome if you feel like there's something wrong with it.
Just one thing I forgot, and this is going to be the name of the tool. So Stupidly, I forgot because we are not that good in marketing, if you noticed. Yeah. But, I mean, he's not. I'm trying to hard, as you can see. But anything else, just talk to us on the end, because most of the talk is pretty like you actually seen it, terminal based, and we invite you to test it because we feel that everybody is like, that's for you for talking a lot and just having too much slides and information, and you never actually work with it, so you don't know that's bullshit analysis. So you need to at least one time show people that actually works. So yeah, that is why we have this. Yeah.
Okay, so on that note, I'd like to jump into the actual detection code of this exfiltration that we were using before. So not actually the data ones, but the beacon ones. So I actually have in one of these machines, I have a PCAP that should, this is great.
It's still sniffing.
Yeah. Okay. So, yeah. As you can probably see, there's a PCAP here called level 0 PCAP. And then I'm just going to show you the detect level 0.py, which is pretty much 13 lines of code in Scapy code to detect this kind of exfiltration. So this is the output of the script. Okay, so it actually found the server responding to an LSLA or LH or whatever, and then the client sent you name A, and then you found the Linux version of what the implant was. So this was just as simple as that. It's 13 lines of code to detect. We built something that was similar to this, but with the assumptions that we had for our model. So our model was, if you find one directional communications between an AP and a station, and you don't find the other way, then you will add this to our candidate problematic AP MAC address list. If you do find it, then you will remove the MAC address from the list. I ran that on a 1.5 million packet capture file, and pretty much got 50 false positives. Because I did not exfiltrate anything, I just ran the tool, it should catch nothing, and then I got 50 cases of exactly that scenario I was talking to you about. So there was an AP, there was a station that was too far away, and your detector didn't actually get to the point that it saw the connection back from that station to the neighboring AP. So again, you're welcome to start trying to use the tool. I'll just demo it very simply over here. Let me just... Okay, so at this point, this is running the server. It will tell you what driver you're running, because if you've ever done anything with wireless, you will know that drivers suck. So you have to actually code around whatever they decided was right for their implementation. So what it's doing right now, it's actually channel hopping and scanning a little bit of the airwaves and trying to see what is around it. So it will find something that it will want to spoof later, after it goes over all of the channels. The client will do the same. The problem is this is supposed to be dropped a long time before the client actually goes and exfiltrates data. So we have to wait a little bit for it to actually set up everything it needs. And after it does this, I can just connect to it. Okay, seems like it's ready. So now we try it on the client, and it does pretty much the same thing, and tries to find something, and then it crashes. Okay, cool. So first mission accomplished, demo fail. I actually know this bug. I just didn't commit the fix, which is awesome. Don't look at my code. My code sucks. Please don't look at it. Don't even look at it. Yeah, it's that bad. So please PR. You will get a link to PR. You can't complain if you won't PR. Okay. Yeah. Okay. Okay. So here we go again. Attempt number 2. So if you have any questions about this, this is your time. Yeah?
Why is your Python code so terrible?
Because I suck at coding. I mean, I'm not a coder. I'm not a developer. I just break stuff. So, yeah. That's
It's
to be
Python,
expected.
what you expect.
Yeah, it's to be expected. I don't know why you expect me to be like a high-quality coder, but okay.
In the future, Golang.
Yeah, perhaps. If you write it. I mean, the point is I just thought this up and thought, yeah, maybe you can track it no matter how crappy the code is. And trust me, this is the good version of the code. I will send you a link to make your eyes bleed if you want.
I think it's great that you have something that works. So
Yeah, it just works. So
mind the naysayers.
yeah. If it works, then it works.
No C over here, Fractal.
Yeah, well, you're welcome to write a C implementation because it could use some speed upgrades. So, yeah. Very nice, very nice. Okay, so that's the connection established. So now we have a bit of a more flexible connection to our Exfiltration server. We have no more problems with length. We have an ACK that can actually tell the server that the client that the server got the request and tell the client lets the server know that it got the response. This is all within the 802.11 framework. So yeah, you will see the AP again. If you go back to the slide where you see the 2 neighboring APs talking to the stations, that will be the station. You will assume that you will see ACKs to the APs. Right? So you will see the APs talking to the stations, and then you will see ACKs coming to the APs, but you don't know which ones. No, I'm sorry, going to the stations. You'll see ACKs going to the stations, because that's the MAC address, the unique MAC address that's derived from the TOTP. So that's how they know that they're talking to each other. Let's try the demessage command again. So now, as you can see, this won't fit in a packet, so it will just be boom, 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 boom. Sending in everything. You didn't get the ACK, so I'm resending, like retrying, whatever. You can still try to track it, and you still won't be able to. So if you got any ideas on how to fix this or how to track this, we're welcome to hear your thoughts. Yes, it's slow, but it works. Yeah, it's Python. So, but we do have over 1 kilobit of throughput, so not that limited. Mm-hmm. Mm-hmm. Excuse me?
Wait. Are we on questions right now?
Yeah, sure,
Yeah?
you can go. After that, you can go to over there and play with it.
Hello.
Yeah.
Nice presentation.
Thank you.
Is this encrypted, right?
Yes, of course.
You're masquerading as WPA traffic.
You just have to encrypt. How do you detect whether it's WPA?
No,
or not?
are you sending the WPA?
Oh yeah,
handshake,
sure,
for
definitely.
instance?
I mean, that's we are looking for APs which are using encryption so that we can actually send random noise and not be suspicious, right?
And do you simulate the WPA handshake for a connecting station? to the
No,
AP?
because you don't know that. You may not know or may not have seen the WPA handshake, but we can totally do that if you want to. But we won't be able to properly do it because if you're on the out-of-scope AP, then you will have to spoof it somehow because you don't know the key. Let's assume that you don't know the key of the AP you're going to spoof. So the handshake will never work, right?
Yeah,
So
but-
either you spoof it somehow
But
or
if I see two stations talking to each other, and
they're not talking to each other. That's the point. You just see 2 APs that are neighboring APs that are talking to 2 stations, but you don't see the traffic back from those stations, right?
Okay, got it.
And this model has been confirmed because, as I told you, I ran just a capture for like 6 or 7 hours in my house, and it's like just ground level, and there's a lot of stuff on the street and offices and all that. And I did see 48 or 50 devices that were in this exact scenario. So you could see the AP talking to them, but you couldn't see the conversation back. So that's the model I was trying to replicate.
And
If you ran the
and the
script,
packets are all the same size. The pattern?
how can they be? If you do ls, then it's just ls. If you do whatever, a big command, then it will be a big packet, right? So at least, at best, it will have like the size of the block cipher, right? So that's the only thing that you can probably use to track it. Yeah, it matches the multiple of whatever the block size is. So perhaps that's a way. But I would like to see your false positive rate on the other kinds of, right? So, yeah. Anyone else?
Talks. Okay.
Isn't it possible to detect by the signal strength?
I was hoping for that question. Yes, it is. However, after talking about this to the creator and firmware writer for the Wi-Fi Pineapple, he told me that there's actually a trick that you can do, which is to modulate the power level at which you send the packet so that the receiving end will see a fluctuating RSSI. So, now what? Right? That's my face when he told me that. I was like,
that's for the outside.
Wow.
If you have like if you have IPs in the corner of the area, you can see if something is inside
but
that
that's
area.
assuming that it will spoof always the same AP, which it won't. Because every time you disconnect, it will scan again and say, oh, now I want to spoof the other one. So how can you actually be sure that...
By detecting neighbor SSIDs that are not the ones that should be inside that perimeter?
How
Like,
do you know?
for example, you have Microsoft Network and you have APs in the corners. And if something from without being Microsoft is transmitting inside the area.
But how do you know that? How do you distinguish the not being Microsoft transmitting inside the area? Because if you are fluctuating the power level, then you're getting the RSSI for something
But
that's
the
a lot further
RSSI
away.
is inside.
No, it's not, because if I'm sending you at a lower power level, then the power,
But
it won't get so
The
far.
corners get that.
Ah, right, yeah, the corners, yeah, that's a good point, yeah. Actually, I didn't think of that, so good one, yeah, that's a nice
Well,
one. The corners is a
I
good
did
one.
think of that. The problem is most of the times we have some scenarios where this don't work. Like one of them was being you don't need any of this if you have the implant, and imagine in a crazy scenario, a silo somewhere in the desert, and you only have one specific IP speaking to one station, then it's no noise. It's impossible for us to...
Yeah, that's the Faraday cage
Yeah,
scenario.
we
It's
can.
just a limitation.
Like, speaking on your example, if we are tracking the area on a specific area, I just don't have a way to emulate anything because they have a concrete white list. That's why I had the logical conditions of what I am expecting to see. There are some scenarios where we can create like applicable solutions for, but like in the future, that is one of the improvements we want to have, is like having this type of scenarios where we can even emulate that or provide some kind of
something we have to work on and emulate and test. The problem is actually creating test scenarios and actually test equipment around all that, especially the corner scenario.
Yeah.
I mean, I don't even know how I would try to set up the detectors and try to go, but that sounds like fun. So probably
sure.
next year we'll have something like that.
Yeah.
More questions?
There.
Thanks for the presentation. I would like to know if it is possible to detect through the TOTP MAC addresses. So
they are valid OUI prefix from the Nmap prefix list, so I will select randomly or just deterministically through the TOTP secret. I will use that to pick one of the vendors and then use that to pick the rest of the termination of the MAC.
And if you guys have the attack installed on that network through the time, a lot of MAC addresses will be detected.
No, because, I forgot to mention that part. If you look here, you will see a message saying stopping TOTP. Why? Because a connection has been initiated, and now it will stay at the MAC addresses it was picked. Because I did notice that, and that's one of the things I fixed, because it couldn't be changing the IPs, the MAC addresses every 30 seconds. That would be a red flag,
Okay.
So when it gets a connection, it stops there. And then when I leave or time out, which just happened, then it will start again the process of scanning what's around it and blah, blah, blah. So you are witnessing it right now.
other things.
That's why we keep the
Yeah.
program running.
More questions?
Okay.
No? Okay.
Go to the station and just try it out on the mobile device
Yeah.
because that is the practical implementation. Yeah.
Yeah.